Want-off factor I. So here want-off factor, it explains about the extent of dissociation or ionization association of solutes in solution. Okay, so how much amount of a solute can be dissociated, that means divide, or how much amount of a solute can be associated, that means combined in a solution, we can study it by taking want-off factor. Okay, so if you want to find this want-off factor, we write like this. Okay, want-off factor, it is represented with I. So if here I is equal to normal molar mass, here molar mass is nothing but molecular weight. Normal molar mass means that is calculated molar mass by observed molar mass. Observed molar mass we taken. Okay, so by using this we can find the I value based on molecular weights. Normal molecular weight by observed molecular weight. Here normal means it is nothing but calculated molecular weight by observed molecular weight. Okay, if we write this want-off factor in terms of colligative property, the relation between molecular weight and colligative property, that two are inversely proportional. That's why these two can be reversed in case of colligative property. So in terms of colligative property, I is equal to, we write observed colligative property. That means observed term we use in numerator, colligative property by, in the denominator now we take normal colligative property we write in the denominator. Okay, by if colligative property values are given, we want to find I value, that is observed by normal, and in terms of molecular weight we take normal by observed. Okay, and here another relation also we have to use, that is I is equal number of moles. In terms of moles, if we write about want-off factor, number of moles after association. Okay, number of moles after association, or it is a dissociation. Okay, that means you take association or dissociation. So number of moles after association or dissociation by number of moles initially taken. Number of moles initially taken, that means initially how much moles you have to taken, that you take in the denominator, and in numerator you write total number of moles after association or dissociation. By using this also we can find want-off factor. Okay, so if you study about want-off factor, we have studied two conditions, one is association, another one dissociation. Okay, right now we can see one by one about this association and dissociation. Okay, so in the two conditions, first we can study about dissociation. Okay, so here you see we studied about dissociation. What is dissociation, how it is takes place. Okay, for that we take degree of dissociation. Okay, here a condition we use, that is degree of dissociation, and here degree of dissociation it is represented with alpha. Okay, so if you want to find degree of dissociation, we take a molecule, and here dissociation means it is nothing but dividing. Okay, so we take AN, it is a molecule, it can be divided into NA, that means A can be divided into N times, number of moles can be increases, it is dissociation. Okay, so here we write in terms of moles, initially moles can be taken as 1, and for product initial moles can be taken as 0. Okay, right. You see, after dissociation or after ionization, when the dissociation process takes place, after dissociation, that moles can be converted into 1 minus alpha, and here it is present n times, so take n alpha. Okay, so after dissociation, here 1 minus alpha is present on reactant side, and their product is n alpha. Okay, and if you want to write total number of moles after dissociation, so if you write total number of moles after dissociation, we can add these two. Okay, if you want to get total number of moles, that two we can add it. Okay, by adding that, you see 1 minus alpha plus n alpha. These are total number of moles after dissociation, right? If you want to find want-off factor, for finding want-off factor, the relation is number of moles after dissociation by initial number of moles. Okay, after dissociation it is 1 minus alpha plus n alpha, and initially number of moles are 1, that's why in denominator we write 1. Okay, so we write like this, I is equal 1 minus alpha plus n alpha. Okay, here we can common alpha, I is equal 1. Here you see we can common alpha plus alpha, we have to common, so here n is present, here minus 1, so 1 we write this side, I minus 1 is equal to alpha into n minus 1. Okay, right. From this, if you get alpha is equal to, right, I minus 1 by n minus 1. Okay, it is a degree of dissociation. So in degree of dissociation, the dissociation alpha is equal to, take I minus 1 by n minus 1. Here I indicate one-half factor and n indicate number of particles on dissociation. On dissociation, how many number of particles are formed, that can be taken in the place of n. Okay, so it is about degree of dissociation. So in degree of dissociation, alpha is equal I minus 1 by n minus 1. Okay, and you see, whenever you see this relation, I is equal to 1 plus alpha n minus 1. Okay, I value, see, 1 plus alpha n minus 1. It means in dissociation I value, it is greater than 1, because I is equal to 1 plus something is present. 1 plus something means it is compulsory greater than 1. That's why in degree of dissociation, one-half factor I value can be taken as greater than 1. Okay, right. Now we can see dissociation. Okay, next we study about degree of dissociation. So you say, association. Right. Now we see here dissociation completed. Next we study about degree of association. So in association means here that molecules can be combining. Okay, that means you take n molecules, these can be combined into single AN. Okay, so here initial moles 1 0. After dissociation it can be present as 1 minus alpha, and here association number is decreases. Association means combining, that's why your number can be decreases. So in that case we write alpha by n. Okay, so here after association, total number of moles after association means we can add these two values. Okay, so in place of n alpha we take alpha by n. Okay, so by taking 1 minus alpha plus alpha by n, in this you see one-half factor I is equal to moles after association by 1. So by 1 means no need to write here. So here I is equal to, we get 1 minus alpha plus alpha by n. Okay, here we can common alpha. By commoning alpha, 1 minus alpha you have to common. So here 1 is present, here minus 1 by n is present. Okay, once you see this relation, in that relation I is equal to 1 minus alpha is present. I is equal to 1 minus alpha means in association I value is less than 1. That's why you write I is equal to 1 minus alpha, 1 minus 1 by n. Okay, and from this I minus 1 is equal to minus alpha, 1 minus 1 by n. Okay, if you common minus, I minus 1 is equal to alpha, 1 by n minus 1, and from this alpha is equal to I minus 1 by n minus 1. Okay, it is a relation for degree of association. Okay, so it is about degree of dissociation and degree of association. In these two conditions we can find I value. In dissociation number of particles increases, in association they can be combined. That means dimer, trimer, tetramer, like that you take. Dimer means n value 2, trimer n value 3, tetramer n value 4, like that you have to take in here. And in degree of dissociation I value is greater than 1, and degree of association I value is less than 1. Okay, right. Now we can see how we can find one-half factors for these like problems. Okay, so we studied by taking an example for this. Okay, see, I will give an example to find one-half factor. You see, calculate one-half factor. Calculate one-half factor for dissociation of Hg2Cl2 in solution. Dissociation of Hg2Cl2 in solution. Okay, so you see what is given, dissociation. Dissociation means dividing. Okay, right. Now we see here another information is also given. It is 80% Hg2Cl2 is dissociated, and here the dissociation percent it is given as 80%. In total it is the problem. Okay, right. If you want to find about this, it is dissociation. So in dissociation alpha is equal I minus 1 by n minus 1. It is the formula we can use. Okay, alpha is equal I minus 1 by n minus 1. Here alpha it is given 80%. 80% means it is nothing but 0.8, and here Hg2Cl2 it is given. Okay, on dissociation it can be present like this, Hg2 plus 2 plus 2Cl minus. Okay, here particle, one particle, Here 2 particles are there. So n value total 3 particles. 1 plus 2, 3. Okay, so in place of n we take 3. By substituting these values, 0.8 I minus 1 by 3 minus 1. 3 minus 1 means 2. 2 this side, right? 2 into 0.8 means 1.6 I minus 1. Okay, from this I is equal to 1.6 plus 1. So it is 2.6. Okay, so for this dissociation, I value can be taken as 2.6. Okay, it is one method. Or if you want to find directly, we use another method also, that we see Vanta factor I is equal to number of moles. Okay, number of particles you take, number of particles dissociated or association we take into alpha plus 1 minus alpha. This is the formula. Okay, so I is equal number of particles dissociated or associated. So here dissociated, so we consider dissociation only. So how many particles it is? 3 particles. So I is equal, we take 3 alpha plus 1 minus alpha. Okay, and you see here alpha value is 0.8. So we substituted in this. So I is equal 3 into 0.8 plus 1 minus 0.8. Okay, 3 into 0.8 means it is 2.4, 1 it is 0.2, so it is 2.6. I is equal to 2.6. Okay, so it is a direct formula for finding Vanta factor in dissociation or in association. Directly we applied. Okay, it is either dissociation or association. We use this formula. According to that, I Vanta factor I is equal number of particles dissociated or associated into alpha plus 1 minus alpha. Okay, by using this formula we can find Vanta factor in dissociation and association. Okay, like these problems are asking in examination, for that we can remember this formula.